And we are live. What is up, everyone? Welcome to the Hack Smarter Twitch channel or my YouTube channel if you're watching this after the fact. Tripping over my words. My name is Tyler. I get to be your host. We get to hang out tonight. I guess you get to choose whether you want to hang out with me. That's your choice, but I will be here. And what we are going to do is we are going to try to get caught up on the TryHackMe Advent of Cyber Challenge. I got way behind, but I have a good excuse. I passed the OSCP. So I took a few days off after taking the OSCP. I did a few of the rooms offline. And then I wanted to stream yesterday, but I got sick. My whole family actually got sick, but I am feeling better today. But the reason I wanted to stream is the room created for yesterday was made by my friend Amoeba Man, who's on the stream. So hi, Amoeba Man. He is a pen tester. He is also a red team content engineer for TryHackMe. Has created some really cool rooms on TryHackMe, including like all of the AD networks. Would encourage you to check those out. But he created a room on Advent of Cyber, actually two of them. The first one was secure coding, and this one is all about hardware hacking, which I have never done in my life. And so my plan is to stumble my way through this. I have not prepped, have not done anything ahead of time. Besides, I started the room because Amoeba Man told me on Discord as I started the countdown, hey, the machine takes like 10 minutes to load. So if you want to follow along, I would encourage you right now, go to TryHackMe and hit start machine on day 19 because it does take some time to load, and we will kind of read through the material as the machine loads. But I would encourage you, if you haven't done this room, let's do it together. Let's stumble through it together. And let me go ahead and share my screen. I will also try to keep my eye over on the chat. I'm going to make my head just a little bit smaller in the corner. There we go. And looking over at the chat. What's up, the dude Henry? What's up, Amoeba Man? Prof X said, hello, how you doing? Congrats on OSCP cert. Thank you, my friend. I am doing well. I was sick yesterday, but I'm doing well today. And the actual walkthrough for this video, or the official walkthrough, is by the great John Hammond. So I would encourage you to check it out. My plan, I didn't want to watch the walkthrough before I did the room myself, so I wanted to stumble through it live. But when I'm done, I'm going to watch John Hammond's video. I'm sure it's excellent, and he probably explains it much better than I ever could. But let's try to stumble through it together and see what we can learn. So we're doing some hardware hacking. Wiggles go burr. Sounds good to me. And as I said before, if you haven't already, go ahead and start the machine. It takes a little bit of time to load. All right, spying on Santa. Elf McSkitty was doing a regular sweep of Santa's workshop when he discovered a hardware implant. The implant has a web camera attached to a microprocessor and another chip. It seems like someone was planning something malicious. We must try to understand what this implant... Sorry, guys, I'm just in my mic. I forgot to turn my mic down earlier. There we go. Let me know on Twitch if everything sounds good. I should tell you guys that. I think it is now. I just had to turn the mic up a tad. We must try to understand what this implant was trying to do. We will deal with the microprocessor and the web camera in future tasks. For now, let's try to uncover what that other chip is being used for. Let's do it. The VM that we will use in this task takes approximately 8 minutes to start. We suggest that you start the machine now to have it ready by the time you get to the practical element of the task. All right, learning objectives. How data is sent via electrical wires and low-level hardware. I'm guessing like zeros and ones, right? Usually that's how you communicate. Hardware communication protocols. How to analyze hardware communication protocols and reading USART data from a logic capture. Welcome to the Matrix. Hardware hacking is often shrouded in mystery and seen as a super complex topic. While there are a lot of in-depth complex hardware hacking components, getting our feet wet is actually pretty simple, especially when it's included in Advent of Cyber. Computers today are incredibly powerful. This allows them to build additional features and safety measures into their communication protocols to ensure that messages are transmitted reliably. Think about the Transmission Control Protocol, TCP, which has multiple redundancies in place. It even sends 3 full packets just to start its communication. In the world of microchips, we often don't have this luxury. To make sure our communication protocols are as efficient as possible, we need to keep them as simple as possible. To do that, we need to enter the world of zeros and ones. I was right. That's like the only thing I know about hardware hacking. This thing begs the question, how does hardware take electricity and generate signals? In this task, we will focus on digital communication. For hardware communication, we use a device called a logic analyzer to analyze the signals. This device can be connected to the actual electrical wires that are used for communication between 2 devices that will capture and interpret the signals being sent. In this task, we will use a logic analyzer to determine the communication between 2 devices in the rogue implant. fascinating. Amoeba Man, I'm curious. Do you do this kind of hacking? I'm not going to give away where you work, but do you guys do this kind of service? Just because I've never seen actual pen tests around something like this. All right, the electrical heartbeat. Back to our question. If we have electricity, how can we generate a digital signal? The approach most hardware components take is to simply turn the power on and off. If the power is on, we are transmitting a digital 1. If the power is off, we are transmitting a digital 0. We call these 1s and 0 bits. Makes sense. To perform communication, we simply turn the power on and off in a specific sequence to transmit a bunch of 0s and 1s. If we send 8 bits, we are sending a single byte. Voila, we have just performed digital hardware communication. These are the wonderful squiggly lines you would see on a logic analyzer. And looking over at the chat, just for those of you on YouTube, I understand you can't see the Twitch chat. That's why you guys should join me live when I do this, but I'll read it for you. That dude Henry said, saw the OSCP video, congrats, thank you again. He said, is this SCADA stuff? And Amoeba Man said, more low-level hardware than that. Like relays and switches, and Amoeba Man said, indeed, yes, we do device reviews of things like point of sales devices and ATMs. Often there you would use this. Oh, answering my question, do you actually do testing like this? Very interesting. So here is our logic analyzer. We got some timing markers over here. I thought this looked like music when I first saw it. Like, I don't know if you guys have ever made music, but this is often what music looks like. You have channels and you're kind of mixing audio levels as you go. So I thought this is some audio thing when I first saw kind of a screenshot of it. We have our measurements here, all that cool stuff. We can transmit text data by using the ASCII table. Sending the binary representation of each character, we can transmit data. However, it isn't actually just that simple. If we wanted 0 effort in our communication, we would need an electrical wire for each 0 or 1 that we wanted to transmit. Considering that a single character is 1 byte of data, thus 8 electrical wires, this can become a mess of wires really fast. To make this more efficient, we need to use fewer wires and then have both hardware chips agree to a specific digital protocol and configuration that will be used to transmit data. Let's look at some of the most common protocols and how they work to send data still while reducing the number of wires we need. Glancing over here, swear, okay. Good chat. I'll just keep moving. USART. Universal Synchronous Asynchronous Receiver Transmitter, USART. I don't know if that's how you actually say it short, is USART. But USART communication, or as it's better known, serial communication, is a protocol that uses 2 wires. One wire is used to transmit data, so TX data from device A to device B, so that's our transmitted data. And the other wire is used to receive data, so TX transmit, RX receive on device A from device B. In essence, we connect the transmit port from one device to the receive port from the other device and vice versa. What is interesting about this protocol is that there is no clock line that synchronizes the communication of the devices. Without a clock, the devices have to agree to the configuration of communication such as the following. Communication speed. This is also called the baud rate or bit rate and dictates how fast bytes of data can be sent. Agreeing to a specific rate tells each device how fast it should sample the data to get accurate communication. While there are fixed standards for baud rates, devices can choose to use any other rate as long as both devices support it. Bit per transmission. This is normally set to 8 bits, which makes a byte, but it can be configured to something else such as 16 bits. Stop and start bits. Since there is no clock, one device has to send a signal to the other device before it can send or end a data transmission. The configuration of the start and stop bits dictate how this is done. And parity bytes, since there can be errors in the communication, parity bytes can be used to detect and correct such errors in the transmission. Let's look through here. Glancing at the chat, see if there's anything that'd be helpful for those of you on YouTube. This is where physical security. Okay, yeah, so that dude Henry said this is where physical security comes into play in side channeling. Amoeba Man said exactly, and not all hardware security concepts are super complex. It becomes complex quite fast, but you can upskill yourself by just starting simple. And he said, I'm doing a better job at these pronunciations than John did. Awesome. I am better than John Hammond at one thing in my life, and that is pronouncing these words that I haven't seen before. Awesome. Once the two devices agree on the configuration of the serial lines that cannot communicate with each other, a single transmission is shown in the diagram below. On the ASCII character of S would be transmitted. 11001010. Oh yeah, so I recognize this a little bit from doing buffer overflow prep for the OSCP, of course, because when you're looking for bad characters, you're kind of going through a list like that. There are a couple of caveats, however. The devices don't really have a way to determine if the other device is ready for communication. To solve this, some USART connections will use two additional lines called clear to send and request to send to communicate to the other device whether it is ready to receive or ready to transmit. Furthermore, to agree upon what voltage level is a binary 1 or 0, a third wire called the ground wire is required to allow the devices to have the same voltage reference. However, despite all of this, USART is an incredibly popular protocol in microprocessors due to its simplicity. SPI, or SPI, the Serial Peripheral Interface Communication Protocol, is mainly used for communication between microprocessors and small peripherals such as sensor or an SD card, while USART communication has the clock built into the TX and RX, remember, transmit and receive lines. SPI uses a separate clock wire. Separating the clock from the data line, I know how to say data at least, allows for synchronous communication, which is faster and more reliable. So the trade-off is adding an additional wire, but we gain a speed and reliability boost. An example of the same S being translated using SPI is shown below. For clock data, clock and data, idle or next byte, and of course we're transmitting S. I'm just rereading this to make sure I'm understanding this. Separating the clock from the data, synchronous communication, which is faster and more reliable, so the trade-off, but we gain speed and reliability boost, is shown below. Okay, I think I understand it. The clock line, so that's right here, tells the receiving device exactly when it needs to read the data line. Two-way communication is also possible, but quite a bit more complex than serial communication. Essentially, one of the devices is labeled the controller. This is the only device that is allowed to send clock signals. All other devices become secondary devices that must follow the controller's clock signal to transmit data back. If two-way communication is used, instead of having a single data line, two lines are used, named peripheral in, controller out, Pico. I once had a dog named Pico, fun fact, which means communication is sent from the controller, and peripheral out, controller in, Poki, which means communication is sent. Okay, so Pico is sent from the controller. Poki is sent from the secondary device back to the controller. Using this, the controller sends a clock signal and a command out to the device using the Pico line. And then keeping the clock signal, the controller receives data back on the Pico line as shown in the diagram below. Okay, I'm trying to just get this in my head. SCK, that's the clock thingy. We have Pico and we have Poki. Okay, so this must be the controller. This is the secondary thing. So clock from controller, controller to peripheral, peripheral to controller, Pico peripheral in, controller out, and Poki peripheral out, controller in. Here's an F and here's an S. Okay. There is one additional change that can be made. That's good. While there can only be one controller, there can be multiple secondary devices. Wouldn't that make them third and fourth devices? To save wires and ports, all devices can use the same SCK, Pico, and Poki lines. A fourth wire called the chip select CS, I can say that, is used to distinguish the device that the communication is meant for. The controller can use this line to indicate to the specific device that it wants to communicate to it, as shown in the diagram below. Use to distinguish a device that communication is meant for. Okay, just rereading it once again. I want to at least kind of understand this. We have our controller here. The chip select wire meant for. Okay, so this is saying each one of these has it. So if we're communicating to peripheral 1, it's going to go through CS1, peripheral 2, CS2, and peripheral 3, CSN, as in whatever number we have there. SPI communication is a fair bit more complex than USART, but having a dedicated clock line increases the speed at which we can communicate and improves reliability. I2C, the Inter-Integrated Circuit Communication Protocol, was created to deal with the drawbacks of both USART and SPI communication protocols. Of course it was, because USART is asynchronous and has the clock built into the transmit and receive lines. Devices have to agree ahead of time on the configuration of communication. Furthermore, speeds are reduced to ensure communication remains reliable. On the other hand, while SPI is faster and more reliable, it requires many more wires for communication, and every single additional peripheral requires one more chip select wire. Obviously, I don't know why you guys didn't know that. I2C attempts to solve these problems. Similar to USART, I2C only makes use of 2 lines for communication. I2C uses a serial data line and serial clock line for communication. Let's see. Oh, it's pronounced I2C. It looks like I2C for what it's worth. Viva Man corrected my enunciation. However, instead of using a chip select wire to determine which peripheral is being communicated to, I2C uses an address signal that is sent on the SDA wire. The address tells all controllers and peripherals which device is trying to communicate and to which device it is trying to communicate to. Once the signal is sent, a data signal can be used to send the actual communication. To notify, I'm curious, man, how long did it take you to put this together? Like the explanations and the actual task, roughly. To notify other controllers and peripherals that communication is taking place and prevent these devices from talking over each other, a start and stop signal is used. Each device can monitor these start and stop signals to determine if the lines are busy with communication. An example of such a data transmission is shown below. All right. Start condition SDA goes low before SCL. Okay? 1 controller is requesting data, 0 controller is sending data. NAC, kind of like SYN-ACK, a 1 in this position indicates that the address peripheral did not respond or was unable to process the request. Okay. And stop condition, SDA goes high. Oh, so we start by going low, we stop by going high. Since an external clock line is used, communication is still faster and more reliable than USART, and while it is slightly slower than SPI, the use of the address signal means up to 1,008 devices can be connected to the same 2 lines and will be able to communicate. Now that we understand the basics of hardware communication protocols, I roughly understand it. We can look to analyze the logic of the rogue implant. Absolutely we can. And Amoeba Man said, was about half a week of work. I know this from my studies, but trying to explain it a bit more simple takes time. Only a half a week. Crazy. Let's keep going. After sending this rogue implant to the forensic lab for analysis, the following circuit diagram is uncovered, and then I message Amoeba Man on Discord telling him to help me with this. That's not included on this task, but this is what I would do if I was one of Santa's elves. So we have this circuit diagram. All right. See some cool wires. I know from playing, if this was a bomb, I know from playing like Counter-Strike Source, it has CS in it. It's kind of like the CS up there. I can defuse a bomb in a game. It kind of looks like a bomb. That's not what it is. We have this webcam peripheral thingy. I have done a little bit with like Raspberry Pi type stuff, which looks similar when you open it up. And I'm looking over at the chat. Amoeba Man said, to summarize, USART uses only 2 wires and no external clock. Okay, USART, 2 wires, no external clock. USART, you have to start. That's how we remember that. There's no external clock. USART will start. I don't know. USART uses only 2 wires, no external clock. SPI has external clock, but needs another wire for each chip you want to connect. That's the CS thing. I2C, IC squared, removes that SPI wire and actually have it transmit an address for the device on the data line. USART, 2 wires, no clock. SPI, external clock, needs another wire for each chip. IC squared removes the SPI wire and actually have it transmit an address for the device on the data line. I think I'm getting it a little bit. Okay, based on the diagram, it seems that there is a microprocessor that is connected to an ESP32 chip. That's exactly what I was going to say. Doing some research, we can see that the ESP32 chip allows microprocessors to communicate over Wi-Fi and mobile networks. So whatever this implant was doing, it was definitely communicating with someone else, the Yeti APT. Who made the name Tyler Ramsbey fan? That's amazing. I'm glad you made that name. If we can intercept this communication between the microprocessor and the ESP32 chip, we'd be able to see what command and information are being sent. It seems like the perfect opportunity for our red and blue team to team up. Elf Forensic and Elf Recon are on the job. And then Amoeba said you can Google ESP32 to check out that chip. Let's do it. Oh, there it is. See? Beautiful. ESP32, Wi-Fi and Bluetooth. A feature-rich MCU with integrated Wi-Fi and Bluetooth connectivity for a wide range of applications, including trying to take down Christmas. Very cool. The elves realize that these chips probably use digital communication that can be intercepted with the logic analyzer. Looking at the wires between the chips. You guys see those wires? We see a black wire connected to a pin called G and D. You guys see that? You can kind of see the N. And a red wire connected to a pin called VIN, kind of like your car's VIN, right? Elf Forensic knows from experience that this would be the ground and voltage in wires, okay? Respectively, meaning these wires are used to provide power to the chip. Got it. That then leaves the green and purple wires, which those are connected to. Oh, look at that. The RX one was receive and this was transmit. So we at least see transmit and receiving there. Interesting. That leaves the green and purple wires that would be used for data transmission. Seeing they're connected to the RXO and TXO pins, Elf Recon can deduce that this refers to transmit and receive lines. I at least got that of USART communication. Hence, we are pretty sure that the protocol used for communication is USART. Let's remember USART. Let me look over at Amoeba Man. He said, to summarize, USART usually only 2 wires and no external clock. Those are our 2 wires right there. Hence, we are pretty sure that the protocol used for communication is USART. Armed with this information, the elves connect the probes of the logic analyzer to the green and purple wires powered on the implant. Immediately, super fast signals are seen on the analyzer. The elves create a logic data dump from the signals, and Mixkitty is asking us to investigate what is actually being transmitted. Let's do it. Analyzing that logic. In order to analyze the logic data dump, we will need to use a logic analyzer tool called... How the heck do I pronounce that? Salia. Let's look up Salia. Start the machine attached to this task if you have not already, which will open an in-browser Windows machine where all the required tools have already been installed for you. Once the machine is loaded on the desktop, double-click the Logic 2 application. Once loaded, you should see this screen. Debug hardware like the pros. That's what we're doing, guys. Just virtually. All right, let's see. All right, assume our machine is ready now. I need to scroll all the way up, though, to show my split view. And sometimes I have to view it in full screen. Come on, I believe in you. Thank you. Looks like it's working now. Beautiful. And we can exit split view here. Let's see if we can get it loaded up. There's our Logic 242 thing. Let's open that up. Do-do, do-do, do-do-do-do-do-do. Get back to our task at hand. Here we are. All right, I clicked it, I think. Yeah, it's just loading, I think. Let's keep reading. Once the machine is loaded on the desktop, double-click the Logic 2 application. Once loaded, you should see this screen. Well, in faith, we believe we'll see that screen shortly. Let's import the Logic data dump to start our analyzer. Select the Open Capture option, select the SANA file that's on the desktop, and click Open. Thank you. We just had to threaten it a little bit, intimidate it. Salia. I'm going to guess Salia. You know, for being a company, you'd think you'd make your name easier to pronounce and understand for marketing purposes. Clay Hack says it's called Slay. Is it really called Slay? Is that really how you pronounce it? Come on, Logic 2. I believe in you. It's the black screen of death. It is 3:30 a.m. wherever this machine is. Okay, we are here. Let's open up a capture. We're going to figure out what that Yeti spaghetti thing was up to. Click SANA. Click Open. Decompressing capture. Preparing session. Getting excited. Dun, 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 dun. Okay, while that does its thing, let's see what else we need to read. You can ignore the calibration error pop-up. Anytime I can ignore errors, that makes me happy. Once loaded, you should be able to see the captures. If you hold left control and use the mouse wheel to zoom out a bit, or you can click on View X Zoom Out, you should be able to see the digital signals. Okay, we can ignore that. Perfect. Welcome to Logic 2. We take privacy seriously and only collect your information. Okay, well, that's fine. It's a cloud computer. And left control and zoom out. There we go. Set up your capture. Next. I don't know. I'm going to follow TryHackMe. They're going to tell me how to do this, I hope. It's a little bit slow on my computer. I don't know if it's slow for you guys following along, but that's probably just because we're running so many things. We'll let it load up a little bit, but we at least zoomed out. I can see the digital signal. Yeah, so I'm seeing similar stuff. We can zoom in a little bit maybe. D0, let's actually analyze this ourselves. It's always good like to kind of look at it and see if you can figure it out. We have D0, D1, A0, and A1. What do you guys think that means? I don't have much of an idea. Can I click it? I don't want to do anything. So we put our mouse over here. We see like duty, frequency, width. We have some measurements over in the top left corner here. We have some second intervals between these different signals. All right. D0 and D1 refer to the digital channels of the two lines that were probed, of course. A0 and A1 refer to the analog data from the probers. Hover your mouse over the first thick line on D1 channel 1 and use left control on the mouse wheel to zoom in again. You should be able to see the entire signal transfer over the first thick line on D1. D1 or D0? Line on D1 channel 1. Okay. D1 channel 1. There it is. Yeah, we zoomed in. I mean, you can zoom in a little more. Zoom out a little more. We missed it. Okay. What is very interesting from the screen is that you can see how the analog voltage data corresponds to the digital data that is seen. Oh, I see. Zoom in, zoom in, zoom in. So it's talking about, we have this right here, and then here's the analog voltage data, I believe is what it's referring to there. Looking at the A1 channel versus the D1 channel 1, you can see that there are slight breaks in the analog data that have been corrected in the digital channel. Now that we can see the digital signal data, we can look to use a logic analyzer to read the contents of the data. Click on the analyzer tabs to the right. Okay. Is that this thing? No? Oh, this is the analyzer thing. Okay, and what am I supposed to click? Click on the analyzers tab to the right. It's already open for us. Perfect. Since we know that the protocol is USART, let's look to configure an async serial analyzer for both channel 1 and 0. Let's configure channel 1's analyzer first. If we were true hardware reverse engineers, we would first have to figure out the rate at which data is being transmitted, as well as a specific configuration such as parity bits and frames. However, to keep this simple, Forensic Elf, aka Amoeba Man, has already discovered this for you. Alter your configuration to match the following and click Save. Okay, well, let's go ahead and do that. I'm going to make my own split view now. Like that. Oh, that might break my thing. It's going to reload it. Maybe I shouldn't have done that. Oh, shoot. All right. There we go. So scroll down. Input channel. Async serial. Right? That first. Okay, 01 channel 1, 4800, 8 bits per transfer, 1 stop bit, no parity bit, least significant bit sent first, non-inverted, mode normal, show. So we're just doing that one. Alter configuration to match the following. Okay, save. Ooh. Let's make this big again and glance at it. So you have all this data information, the start, the duration. Interesting. Where the heck did TryHackMe go? Right here. Okay, once saved, we can see the data is being analyzed. Click the little terminal icon and we can actually read the data being transmitted. Really? Click the little terminal icon. Ooh. Do I need to click something else to see other data? So like if I click this one and then click that, is it different? Okay, let's go back to the instructions. Terminal icon, we can actually read the data being transmitted. Yep, we see the initialization sequence of the serial line and then 3 lines of data being set. Drink of water. Yo, you guys see the weather where I live? On Thursday, the high is like negative 15 degrees Fahrenheit. With the wind chill be negative 50 degrees Fahrenheit. What a beautiful place to live. Once saved, we can see data. Okay, we see the initialization sequence of the serial line and then 3 lines of data being sent. ACK reboot, CMDX19583799600. Okay. This doesn't yet mean anything since we are only seeing one side of the data. In order to see the other messages, we need to add another analyzer to channel 0. Click the plus icon next to analyzers and add another async serial analyzer with the same configuration except for channel 0. All right, let's see if we can do this from memory. We will go to async serializer. Go back to this. Oh, maybe plus? Oh, I don't know what I'm doing. Async? Okay. Yeah, I did it right. Go back to here. So we're doing this to channel 0. So let's change this over to channel 0. And it actually kept all of our stuff in here. 4800, 8 bits, 1 stop. That all looks correct. Hit save. Wonder if I did that right or not. Happens if we click our terminal. Oh yeah, we got, hello, command. Please send security string. Security string accepted. Please specify new baud rate. New baud rate of 9600 accepted. And then we're saying some ASCII characters. I wonder if we can convert those or something. I don't know. Once added, click the trash icon in the bottom right to remove all terminal data. Oh. Well, I didn't do that. Trash icon in the bottom right. I don't know. It looks fine to me. Now we are starting to piece together the information. It seems like the microprocessor is establishing a session with the ESP32 device to allow communication to the control server. We can now see the full discussion between the two devices. The processor asked the ESP32 to reboot its connection to the control server. The ESP32 is happy to oblige, but requests a security code to be sent to allow connection to the control server. Once the security code has been transmitted, the ESP32 allows the microprocessor to negotiate a new baud rate to be used for communication. Interestingly, once this new baud rate is accepted, we cannot read the rest of the output. However, since we intercepted the baud rate, we can simply edit our channel 0 analyzer to a new baud rate to read the rest of the communication that was sent. Go make this change and get your flag. Okay. So let's go back to our thing. The new baud rate of 9600 was accepted for channel 0. I don't remember which one of these was channel 0. I think that's channel 1. If we edit this one, no, that's channel 1. Okay, close that out. Edit this one, and we're going to change our baud rate, also known as the bit rate, to 9600. Hit save. Ooh, THM hacking hardware is fun. There is our first flag, ladies and gentlemen. If I could copy it, that would be a good starting point. Okay, can I Control C? Might just have to type it. That's okay. This is excellent progress. We were able to read the initial communication between the two devices that were used to establish a connection to the control server. Now that we have this information, we can keep monitoring the lines and analyzing the logic to see if any messages that are sent. We are one step closer to knowing who is responsible for this rogue implant. Where do we drop our flag? Let's just do that first. All right, now let's see if we can answer these other questions. Whew. What device can be used to probe the signals being sent on electrical wires between two devices? The logic analyzer or something? Is it logic capture? Logic analyzer. Maybe I just spelled it wrong. That's probably what happened. Scrolling. Oh no, I spelled that right. Is it logic capture? LOGICANALYZER. Oh, UK spelling. THM is British. I don't know the UK spelling of logic analyzer. Shoot. Oh, with an S? What weirdos. Even though they're the ones who came up with the language. I'm doing the American way. I wonder how many people got thrown off by that. USART is faster than SPI for communication. USART is faster than SPI. I think so. Oh, no, it's not. Let's refresh our understanding. To summarize, USART uses only 2 wires and no external clock. SPI has external clock but needs another wire for each chip you want to connect. IC squared removes that SPI wire and actually have it transmit. So SPI is faster than USART. USART communication uses fewer wires than SPI. Well, yes, we just said that. USART is faster than IC squared for communication. IC squared moves that SPI wire and actually have it transmit an address for the device. I don't think so. IC squared uses more wires than SPI for communication. IC removes that SPI wire and actually have it transmit. No, I don't think so. SPI is faster than IC squared for communication. I'm going to say no because I say it's an improvement on the other ones. Oh, shoot, it is. So SPI is the fastest. What is the maximum number of devices that can be connected on a single pair of IC squared lines? It's like, can I remember this? It's like 1,080 or something. No, I know it's something like that. I remember reading that. And a meme man said, remember, IC squared must send an address, so slower, but trade-off is less wires. That makes sense. Let's see if we can find the one. I could have swore it was like 1,080. I probably mixed the numbers up in my head. IC squared. 1,008. Look how close I was to going off memory, ladies and gentlemen. I said 1,080. It was 1,008. I was so close to having that from memory. So close. Just had two numbers mixed around. What up, J Money? What is the new baud rate that is negotiated between the microprocessor and the ESP32 chip? It was 9,600, wasn't it? Look at my memory. We completed hardware hacking, and I was planning on getting caught up, but that's a lot of learning. I think we'll pause on hardware hacking, and I might try to get caught up on some of these other rooms offline. For those of you who have been hanging out with me, you know that I also am going on a series of learning Rust programming, literally just for fun. We did 2 hours of Rust programming earlier in the week, and my goal is to hit kind of a chapter each time that I stream. So I will be doing Rust programming coming up soon as well. Try to get caught up on Advent of Cyber. I don't really have a set schedule on when I'll be streaming. What day is it today? I don't even know. Tuesday? I'll probably stream tomorrow and Thursday. Friday, I'm doing Among Us VR with some people I work with. We're going to practice our deceit and trickery on Friday. But guys, thank you for hanging out with me. It looks like someone just raided us, but I'm actually signing off, so I apologize for those of you who just got to my channel. Make sure you come back. I do ethical hacking walkthroughs. I'm going through Rust programming. I'm a pen tester, and I enjoy hacking stuff. But unfortunately, you guys are joining at the end of the stream. Tyler Ramsbey fan said Tyler is very underrated. I'm glad you say that, since you are the Tyler Ramsbey fan. Thank you for the kind words. And Amoeba Man said, so proud of you, Tyler. First implant you've analyzed. Yes, and honestly, Amoeba Man, excellent job on the room. You did a really good job explaining it, explaining a topic that I think is complex. I learned some stuff from it. And if I ever have to hack an ATM, I'll make sure I message you on Discord first, because I still won't know what I'm doing. But thank you for the room. Thank you for all the things that you've done on TryHackMe. And for all of you watching, thank you again for hanging out with me this evening. I will catch you guys hopefully tomorrow night if I stream. I'll see you guys later. See ya.